The cosmic horizon. Every journey begins with a horizon. For sailors of old, it was the line where sea met sky, a boundary suggesting both limit and promise. For humanity today, the greatest horizon is not on Earth, but in the cosmos, the edge of the observable universe. Defined not by land or sea, but by light itself, this horizon marks the farthest distance from which information can reach us. Beyond it lies silence, not because nothing exists, but because light from there has not yet had time to arrive. The observable universe spans an astonishing 46 billion light-years in every direction. At first glance, this seems paradoxical. After all, the universe is only 13.8 billion years old. But because space itself expands, distant galaxies are carried away on the swelling fabric of the cosmos, stretching the light's journey. What we see when we look outward is not the present, but a vast history. Each photon is a messenger from the past, traveling billions of years to tell us what once was. The contrast between human and cosmic horizons is striking. A traveler on Earth sees the horizon shift with every step, always retreating but always near. It is intimate, measurable, and tangible. The cosmic horizon, by contrast, is unfathomably remote, an invisible wall written by the laws of physics. Where a sailor's horizon offers the promise of new land just beyond sight, the cosmic horizon suggests something more humbling. There are regions of the universe forever inaccessible, beyond communication, beyond knowledge. Yet this cosmic boundary is not meaningless. It defines the stage on which all of human history, and indeed all known physics, plays out. The galaxies, stars, and planets we can observe fall within this sphere. Our theories, experiments, and telescopes are confined to what light has carried to us. In this sense, the horizon is not just a limit, but also a map, telling us where our questions may reach and where they must yield to silence. Philosophically, the cosmic horizon forces us to reflect on the nature of knowledge. We like to believe reality is knowable in its entirety, that patient science can uncover every corner. But the horizon says otherwise. There are truths forever hidden, places we can never see, events we can never confirm. The universe is larger than observation, and our vision is bounded by the speed of light. Yet within this boundary lies wonder. To know that the observable universe stretches 46 billion light-years is not a defeat, but a triumph of imagination and science. It is a horizon we may never cross, but one we can describe, measure, and marvel at. Where human horizons invited exploration of seas and continents, the cosmic horizon invites exploration of thought, theory, and humility. Thus, the cosmic horizon is more than a physical limit. It is a metaphor for our place in the cosmos, finite beings in an infinite expanse, reaching always toward the edges, aware that beyond every horizon lies another mystery waiting to be dreamed. Looking back in time, when we look at the night sky, it feels immediate. Stars twinkle above as if they shine for us in the present moment, their light pouring down in real time. Yet the truth is stranger and far more humbling. To look outward is to look backward. Every photon that reaches our eyes has traveled across space and time, carrying with it the memory of where it came from. What we see is not how things are, but how they were. Astronomy is therefore less a study of the present than an exploration of deep time, a cosmic archaeology written in light. And if the moon, bright and familiar, is already old news when we see it, its glow has traveled just over 1 second to reach us. The sun, so central to our lives, is revealed to us as it was 8 minutes ago. When we gaze at Sirius, the brightest star in the night sky, we witness light that began its journey nearly 9 years earlier. Already, immediacy fades, replaced with echoes, but as we stretch our gaze further, the scale of this temporal dislocation grows staggering. The Andromeda Galaxy, visible on clear nights as a faint smudge, appears as it was more than 2 million years ago when our ancestors first shaped tools from stone. Farther still, the Hubble Space Telescope has captured galaxies whose light began its journey billions of years ago, long before Earth itself existed. In those images, we are seeing the universe's childhood stars igniting in clouds of hydrogen, galaxies colliding in primordial violence, structures forming that would someday give birth to worlds. The contrast between immediacy and deep time is profound. In daily life, we live within the present. A conversation unfolds in seconds, decisions shape hours, memories stretch back decades. Time is intimate, human-scaled, tied to the rhythms of breath and heartbeat. But the universe cares little for immediacy. Its timescales dwarf our own, stretching across billions of years. Every glance at the sky places us not in the present, but in a continuum where past and present blur into a single view. This temporal dislocation reshapes our sense of reality. We cannot know what distant galaxies look like now, because now has no meaning across such distances. Light takes so long to travel that the present of those galaxies is forever inaccessible to us. The cosmos is a patchwork of pasts. Near stars in the recent past, distant galaxies in the ancient past, and the cosmic microwave background revealing conditions 8 billion years ago. To observe is not to witness reality as it is, but reality as it was layered, staggered, and incomplete. Philosophically, this truth forces humility. We often assume our perceptions reveal the world as it is, immediate and true. Yet the cosmos teaches otherwise. All seeing is delayed, all knowledge provisional, all vision limited by the finite speed of light. Even here on Earth, to see a friend across a room is to glimpse the microseconds in the past. In daily life, the delay is negligible. On cosmic scales, it becomes overwhelming, turning observation into time travel of a peculiar kind. And yet, within this strangeness lies wonder. To look back is to witness the universe's autobiography unfolding across epochs. Every telescope is not just an instrument of vision, but a time machine, allowing us to reconstruct the great story of creation. Our immediacy is fleeting, but the light from distant galaxies connects us to eras unimaginably remote, binding the present to the depths of cosmic history. Thus, when we look at the stars, we do not see them as they are, but as they were. Though our night sky is a museum of ancient light, and we, its visitors, walk among relics billions of years old. In every glimmer we find not just beauty, but time itself made visible. The curtain we cannot pull back. Every horizon tempts us to cross it. On Earth, sailors once believed the sea's edge hid monsters, yet they sailed anyway. Mountains rise as barriers, and we climb them. Deserts stretch endless, and we cross them. Again and again, humanity has answered limits with defiance. But the cosmos presents us with a limit of another kind, the boundary of the observable universe. Beyond it, light has not had time to reach us. Beyond it, we know there is more, yet we cannot see. Here lies the cosmic curtain drawn tight, daring us to imagine what lies behind. The weight of this boundary is profound. The observable universe extends 46 billion light-years in every direction, but that sphere is not the cosmos in its entirety. It is merely the part we can access, a window framed by light's finite speed and the universe's finite age. Beyond the curtain stretch realms forever hidden, galaxies whose light will never touch us, events we cannot measure, truths we cannot test. Unlike mountains or seas, this is not a barrier we can conquer with better ships or sharper tools. It is a boundary woven into the fabric of reality itself. The contrast between our instincts and this immovable limit is stark. Our species thrives on exploration, fueled by the belief that every frontier can be breached. The cosmic curtain denies that optimism, telling us there are horizons we will never pass. It is the humbling recognition that the universe is not fully ours to know. The curtain is not a wall we can climb, but a silence we must accept. And yet, this silence is not empty. It is suggestive. Knowing that more exists beyond what we can observe ignites speculation. Perhaps endless galaxies, parallel structures, or even entirely different physical laws await. The curtain fuels imagination precisely because it cannot be pulled back. It transforms the unseen into possibility, and possibility into wonder. In this sense, ignorance becomes fertile ground, not failure. Philosophically, the cosmic curtain reminds us of our condition as finite beings in an infinite reality. We like to believe knowledge can expand until nothing is left unknown, but the curtain insists there are truths forever beyond reach. To live with it is to accept mystery as permanent, not temporary. This is not defeat, it is perspective. It teaches us that humility must accompany curiosity, and that the unknown is not a flaw in our knowledge but a feature of existence itself. Thus, the curtain we cannot pull back is not a barrier against meaning, but a source of it. It tells us that the cosmos is larger than our instruments, larger than our minds, larger even than our dreams. To stand at the edge of the observable universe is to face both frustration and awe, knowing that the greatest truths may always remain hidden, yet that their very hiddenness is what gives our search its infinite depth. Galaxies, clusters, and filaments. When we zoom out far enough, the universe reveals a structure so immense it defies ordinary imagination. The cosmic web. Galaxies are not scattered randomly across space, but woven into patterns of breathtaking order. They gather into groups. Groups merge into clusters. Clusters stretch into filaments, thread-like bridges that span hundreds of millions of light years. Between these filaments lie vast voids, regions so empty they dwarf entire galaxies. What emerges is a tapestry on the largest possible scale, a universe at once structured and hollow, ordered and desolate. At the most familiar scale, we see galaxies, spirals, ellipticals, and irregular forms, each home to billions of stars. Yet galaxies are not isolated islands. Gravity draws them together, binding them into clusters. The Virgo cluster, for example, hosts thousands of galaxies, each swirling with its own stars and planets. These clusters, in turn, link to one another, stretched along filaments of dark matter and gas, forming bridges across space. The result is a lattice, a cosmic architecture spanning billions of light years. The contrast between order and emptiness here is striking. Filaments blaze with activity, galaxies colliding, stars forming, black holes feeding. Yet adjacent to these structures are voids so vast that entire superclusters could drift inside them with room to spare. Within these voids, only a few lonely galaxies exist, surrounded by darkness. The web is not uniform fullness, but stark asymmetry, where abundance and emptiness coexist in tension. This duality raises profound questions. Why should matter arrange itself into such patterns at all? The answer lies partly in the physics of the early universe. Quantum fluctuations stretched by cosmic inflation-seeded regions of slightly higher density. Over billions of years, gravity amplified these tiny differences, pulling matter into filaments and leaving voids behind. What began as ripples in primordial plasma has become the grandest architecture ever known. Philosophically, the cosmic web blurs the line between chaos and design. On one hand, its structure emerges naturally from physics, requiring no guiding hand. On the other, its elegance evokes the artistry of a woven fabric, as though the universe itself were spun from invisible thread. To stand before such immensity is to feel both awe at the order and vertigo at the emptiness. The filaments remind us of connection, the voids remind us of isolation. On human scales, order comforts us. We seek patterns, coherence, structure. Yet the cosmic web insists that structure and emptiness are inseparable, two halves of one reality. Galaxies shine in clusters, but between them yawns a darkness almost unimaginable. This juxtaposition teaches us that the universe is not simply full or empty, ordered or chaotic. It is both, layered across scales we are only beginning to comprehend. Thus, the cosmic web stands as the grandest known structure, a map of matter, stretched across the cosmos, binding galaxies into threads of light while leaving vast regions bare. It is at once a triumph of order and a testament to emptiness, a reminder that even in the largest patterns the universe balances presence with absence, fullness with void. the cosmic microwave background. If the cosmic web is the universe in its maturity, the cosmic microwave background is its baby picture, the oldest light we can ever see. This faint glow, stretched into microwaves by billions of years of cosmic expansion, is a snapshot of the universe when it was only 380,000 years old. Before that time, matter and radiation were so tightly intertwined that light could not travel freely. The cosmos was an opaque plasma, a fog of charged particles scattering photons in every direction. When the universe cooled enough for atoms to form, light finally decoupled, and that ancient glow has been streaming through space ever since, carrying with it a record of the universe's first moments of transparency. Today, the cosmic microwave background, CMB, bathes the cosmos in every direction. Invisible to our eyes, it can be detected with radio telescopes as a near-uniform sea of microwave radiation. At first glance, it appears smooth, the same temperature to within a fraction of a degree. But closer inspection reveals faint ripples, tiny variations in density that would later grow into galaxies, clusters, and filaments. In those minute fluctuations lies the blueprint of the entire cosmic web, written into the fabric of light itself. The contrast between the youthful cosmos and the present cosmos is profound. The CMB shows us a universe that was hot, dense, and almost unimaginably simple. No stars, no galaxies, no planets, only hydrogen, helium, and the seeds of future structure. It was a cosmos defined by potential, a vast canvas awaiting the slow brushstrokes of gravity. The present universe, by contrast, is rich and complex, filled with stars burning elements, black holes warping space-time, and planets hosting life. From the simplicity of the CMB has emerged the dizzying intricacy we now inhabit. This contrast is also temporal. To observe the CMB is to look back nearly 14 billion years, glimpsing a moment so remote that it redefines the very concept of history. Human history spans thousands of years. Civilizations rise and fall over centuries. Even Earth itself is only 4.5 billion years old. Yet the CMB predates all of it. It is the oldest fossil of light, a record not of human striving, but of cosmic becoming. Every telescope tuned to its faint hum is a time machine connecting the present to the dawn of creation. Philosophically, the CMB is both humbling and intimate. Humbling because it reminds us how young our species is, how brief our existence compared to the universe's lifespan. Intimate because the very atoms in our bodies trace their ancestry to the fluctuations recorded in that ancient glow. Without those tiny ripples in the CMB, there would be no galaxies, no stars, no life. In its patterns lie the origins not only of the cosmos, but of us. The CMB also represents a limit. Beyond it lies the opaque plasma of the infant universe, a curtain we cannot see through with light. The CMB is thus both revelation and boundary. It shows us the cosmos at its birth, yet conceals whatever came before. Inflation, quantum fluctuations, even the possibility of other universes all remain hidden behind that wall of radiation. The youthful cosmos speaks to us, but only in part. Thus, the cosmic microwave background is our ultimate snapshot, a glowing photograph of the universe's childhood, imprinted on the heavens themselves. It bridges the simple and the complex, the past and the present, the possible and the unknowable. To study it is to read the first page of a story still being written, a story in which we improbably have become conscious narrators, gazing back at the light that made us possible. The expanding stage. The universe is not static, it expands. This truth, first glimpsed by Edwin Hubble in the 1920s, overturned the long-held assumption of a steady cosmos. Galaxies are not fixed in place but recede from one another, carried outward by the stretching fabric of space itself. At first, scientists imagined this expansion would gradually slow, tugged back by gravity's pull. But in 1998, observations of distant supernovae revealed something astonishing. The expansion is not slowing at all, it is accelerating, driven by a mysterious force we call dark energy. Suddenly, the stage of the universe was no longer simply growing, it was racing outward faster and faster, as if pulled by an invisible hand. This accelerated expansion reshapes how we think of the cosmos. It means the universe is not just vast but dynamic, and that its future will not converge toward collapse, but diverge into greater emptiness. Galaxies that are now visible will one day drift beyond the cosmic horizon, their light stretched until it can no longer reach us. The observable universe will shrink in content even as space itself grows. We live then at a privileged moment, able to see a richness of galaxies that future observers will never witness. In time, cosmic history will vanish from view, swallowed by acceleration. The contrast between the stage we see now and the one to come is dramatic. Today's universe is luminous, filled with galaxies, clusters, and webs of light stretching across billions of light years. Yet in the far future, the expansion will isolate each galaxy, stranding civilizations in pockets of solitude. The cosmic stage will persist, but its actors will fade from sight, leaving only silence and emptiness. To know this is to feel both awe and melancholy. Awe at the grandeur of the expanding stage, melancholy at the recognition that we are witnessing a fleeting chapter in cosmic visibility. Philosophically, accelerated expansion also reframes our understanding of beyond. Beyond the observable universe lies a reality we cannot see because light has not yet reached us. But now there is another beyond, galaxies slipping away into permanent invisibility. Not because of time, but because of expansion. It is a dynamic curtain constantly redrawn, erasing regions from our future view even as they exist in the present. The universe is not only larger than what we see it is in the process of making itself inaccessible. This raises a profound question. What lies outside our cosmic reach? If expansion is accelerating, then there are realms we will never touch, not with light, not with signals, not even with imagination rooted in causal contact. The beyond becomes not merely a spatial frontier, but a temporal and existential one, forever separating us from most of reality. In this sense, the expanding stage is both a revelation and a reminder of limits, yet within those limits lies meaning. To exist in a universe that expands is to live within a story of becoming, where the stage itself is growing faster than its actors can follow. It is a cosmos that insists on change, denying permanence, pushing us to accept impermanence as fundamental. The accelerating expansion is not a flaw, but the very rhythm of the play, and we are privileged to glimpse it while the stage is still full of light. Thus, the expanding stage sets the mystery of the beyond. It shows us a universe that grows ever larger, ever emptier, and ever more mysterious. To live within it is to recognize that wonder lies not only in what we can see, but also in what we must accept we will never reach. More of the same. Perhaps the most unsettling thought about the cosmos is that beyond the cosmic horizon, it might be just more of the same. More galaxies, more stars, more dark voids, and more cosmic webs stretching endlessly outward. We look at the vast expanse before us and marvel at the rich tapestry of light, galaxies, and clusters. But what if just beyond the horizon, all we encounter is the repetition of what we already know? More galaxies swirling in their dance, more distant suns burning in the darkness, more empty space between. The enormity of it all, so full of wonder, becomes strangely banal. This possibility challenges the awe that the cosmos normally evokes. We look up and are filled with wonder at the complexity and scale of the universe, the knowledge that we are part of something far larger than ourselves. But what if this wonder is simply a fleeting glimpse of a greater cosmic redundancy? As we peer deeper into space, might we see just another spiral galaxy, another cluster, another void stretching endlessly? The universe in this light might seem like a vast, infinite repetition, a cosmic echo that leads nowhere new. The contrast between banality and awe here is sharp. Awe invites us to see the infinite as something meaningful, a mystery waiting to unfold, a playground for discovery and exploration. But banality suggests that all this cosmic beauty might be meaningless, a vast mechanical machine endlessly spinning its wheels. The possibility that the universe is not a grand narrative but a seemingly infinite repeat of the same process strains our romantic view of exploration. Instead of new frontiers, we face an endless stretch of the known, a galaxy stretching into galaxies, like a labyrinth with no exits. Yet even in the face of this possibility, there is a strange beauty. For even if the universe is a vast, unending replication of cosmic patterns, that very repetition is still awe-inspiring. To imagine that beyond our grasp there are more stars burning in the same way, more galaxies swirling into infinity, is to realize that the universe is far more stable, far more enduring than we might have ever imagined. The fact that these patterns repeat across such vast distances, across such immense stretches of time, speaks to the immense, unyielding consistency of the laws of physics. It is an order that persists whether we perceive it as grand or banal. In this sense, the vast cosmic repetition forces a philosophical reflection. Does meaning lie in the new or in the enduring? Is it the uniqueness of individual galaxies that gives us awe, or the fact that the same cosmic forces create them again and again, tirelessly across the universe? Perhaps the true wonder lies in the stability of these processes, in the fact that galaxies, stars, and life emerge wherever conditions are right. So, the horizon beyond may indeed be filled with more of the same. Yet the very fact that the same cosmic processes can unfold across billions of light years, across infinite stretches of time, offers a kind of beauty in its simplicity. The universe is not just an endless repetition, but an endless act of creation, a cycle of rebirth, of cosmic continuity that fuels both wonder and reflection. Cosmic variance. The universe, as we know it, appears vast yet eerily uniform. When we look to the farthest reaches of space, we find galaxies scattered across the cosmos in a seemingly regular pattern stretched out along the filaments of the cosmic web. The laws of physics appear constant, universal, forming the backbone of cosmic order. But what if the universe is not as uniform as it seems? What if different regions, isolated from each other by vast stretches of space, are governed by distinct conditions, unique histories, and even diverging physical properties? Such cosmic variance, where different regions of the universe experience wildly differing densities, formation histories, or even fundamental constants, could redefine our understanding of reality itself. Speculation about cosmic variance introduces a fascinating contrast: uniformity versus local chaos. On the grandest scales, the universe appears to follow the same set of rules. Galaxies form, stars burn, and black holes grow. These processes seem to repeat across billions of light years. But beneath this uniformity, the universe might not be the same everywhere. Some regions may be denser, with more galaxies packed tightly together, while others may be stretched so thin that the nearest galaxy is tens of billions of light years away. In certain parts of the cosmos, the formation of stars might be slower or faster than in others, due to local conditions like the amount of dark matter or cosmic radiation. Some regions may even experience different values for fundamental constants, such as the fine structure constant or the speed of light constants, that in our corner of the universe we assume are fixed. This idea shatters the comforting image of a homogeneous cosmos. Imagine for a moment that the universe's vast stretches contain realms of existence so different from one another that life itself, or even the laws of physics, might look alien depending on where you are. What if in some distant, unexplored region, gravity behaves differently, allowing stars to burn with colors we cannot even comprehend? Or what if in other regions, matter is so dense that black holes are born rapidly, altering the entire fate of a galaxy? In such zones, the life cycles of stars, galaxies, and even the fabric of space-time itself could unfold in unexpected ways, governed by forces and conditions foreign to our understanding. The contrast between uniformity and chaos is a theme that has echoed throughout science and philosophy. For centuries, the idea of a homogeneous universe was a pillar of scientific thought. The discovery that the universe was expanding, that distant galaxies were receding from us, hinted at a dynamic and evolving cosmos. But now, as our observational tools peer deeper into space, we are faced with the possibility that the universe is far more chaotic, more variant than we could have ever imagined. The smoothness we observe might be a fleeting illusion, obscured by the vast, empty stretches between galaxies. Local differences in density, temperature, and even the laws of physics could mean that the universe is far from uniform. It is a patchwork of regions, each with its own unique characteristics, struggles, and histories. Philosophically, this idea challenges the very notion of what it means to be universal. If fundamental constants vary across the cosmos, what does that say about the universality of our own existence? Are we, in some sense, the lucky inhabitants of a region of the universe where conditions are just right for life as we know it? The possibility of local chaos raises intriguing questions about our place in the larger fabric of reality. It forces us to confront the humbling idea that the universe's story may not be a single, linear narrative, but a series of parallel histories unfolding simultaneously in different parts of space. Moreover, the notion of cosmic variance calls into question the limits of our understanding. How can we claim to know the fundamental nature of reality if it may not even be the same everywhere? Our science, our physics, is based on the assumption that the laws we observe here on Earth apply throughout the cosmos. But what if that assumption is wrong? Could different regions of the universe harbor forms of existence we can scarcely imagine? In the end, cosmic variance invites us to rethink our vision of the universe not as a monolithic entity, but as a collection of ever-evolving, ever-different regions, each with its own rules, its own time, and its own story. It suggests that the universe's true complexity lies not just in the vast stretches of space, but in the subtle differences, the hidden histories, and the local diversities that make each part of the cosmos a unique and dynamic entity. The end of familiar laws. As we peer deeper into the universe, we approach the cosmic horizon, a boundary beyond which lies a vast expanse of reality we will never see. But what if the laws of physics themselves change beyond this horizon? Could the very principles that govern the universe here, in our corner of space, break down or evolve as we venture farther out? This question challenges the very foundations of physics and forces us to confront the possibility that our understanding of the cosmos might be limited not just by distance or time, but by the inherent nature of the universe itself. In the observable universe, the laws of physics have proven remarkably consistent. Gravity, electromagnetism, and the nuclear forces all behave according to well-established principles. The constants of nature, like the speed of light, Planck's constant, and the gravitational constant hold steady, giving rise to a predictable, coherent universe. However, these laws are based on observations within a specific range of conditions, close to our region of space and time. What happens when we venture beyond that into areas that are vastly different from our own? Could the laws of physics themselves adapt, shift, or even cease to operate in the same way? This possibility hinges on the nature of the cosmic horizon itself. Beyond it, the universe's expansion accelerates so rapidly that distant galaxies are receding from us faster than the speed of light. This creates a kind of barrier where information cannot travel back to us. If we cannot observe these distant regions, we have no way of confirming whether the laws of physics behave in the same way there. For all we know, distant regions might harbor different physical constants or forces that behave in ways we cannot yet imagine. The physics we know might be mere local rules applicable to our small corner of the universe, but not universal in the strictest sense. Philosophically, this raises profound questions about the nature of the universe itself. Are the laws of physics truly universal, as we've assumed, or are they contingent, dependent on where and when they are observed? The potential for differing physical laws beyond the horizon forces us to confront the limits of human knowledge. It suggests that our understanding of reality is not final but provisional, always subject to the possibility of new revelations, new discoveries, and new understandings of the cosmos. In a universe where physics could change beyond the horizon, what does it mean to say something is true? If the constants of nature are not truly constant but vary depending on the region of space, does that make them less true? Or is it simply that the scope of our knowledge is too small to grasp the full complexity of existence? The end of familiar laws is not a defeat, but a reminder of the vastness of the unknown. It challenges the human desire for certainty and mastery, replacing it with a more humble acknowledgement of the limits of our understanding. It forces us to ask not just what the universe is, but how it might be, how it could evolve, how it could shift, and how we are only beginning to scratch the surface of its infinite complexity. The early universe's sudden growth. The early universe was not always the smooth, structured cosmos we observe today. In fact, it began in a state of extreme chaos, a seething hot soup of particles and radiation. But something extraordinary happened in the moments after the Big Bang. The universe underwent an epoch of rapid expansion known as inflation. This brief, yet mind-bogglingly swift growth transformed the infant universe, smoothing out its irregularities and setting the stage for the structured cosmos we now observe. Inflation was a period where space itself expanded exponentially, faster than the speed of light, in a fraction of a second. It was a chaotic, violent process that ultimately led to the ordered result of galaxies, stars, and life. Inflation is a key component of the Big Bang model, explaining many of the peculiarities of the universe's current structure. The theory proposes that during the first tiny fraction of a second, the universe expanded by a factor of at least 10 to the 26 times its size. This was a period of extreme chaos, particles, radiation, and forces racing apart, driven by a mysterious energy field thought to be associated with the potential energy of a field known as the inflaton. During this period, the universe's size grew faster than light could travel, a scenario that seems to break the rules of relativity but is actually allowed due to the fact that space itself was expanding, not objects moving within it. The chaos of inflation, however, set the stage for remarkable outcomes. First, inflation smoothed out the universe in a way that gravity and other forces could not. Without inflation, the universe would have been left with imperfections, regions of slightly higher or lower density, leading to the formation of clumps of matter and radiation. But inflation stretched these irregularities out to such an extent that the universe became remarkably uniform, with very little variation across vast distances. This is why when we look at the cosmic microwave background, CMB radiation, we see it as nearly uniform across the sky, with only minute fluctuation. Inflation took the chaotic, turbulent birth of the universe and transformed it into the smooth backdrop that would later give rise to stars, galaxies, and clusters. The process of flattening is equally important. After inflation, the universe's geometry was radically altered. Any initial curvature of space was flattened as the universe grew so rapidly that the large-scale structure of space itself became almost perfectly flat. This has profound implications. The idea of a flat universe means that the sum of all angles in space adds up to 180 degrees. Essentially, the universe behaves as though it follows the geometry of Euclidean space. The result is a universe that appears very large but is also governed by predictable, uniform laws. This flattening effect helps explain why the universe appears so homogeneous on large scales, with galaxies scattered across vast distances but still following the same physical rules everywhere. The contrast between the rapid chaos of inflation and the ordered result we see today is striking. The early universe was a tumultuous, violent period of growth, with forces at play that we cannot fully comprehend. And yet from this chaos emerged the beautifully structured universe we observe, with its cosmic web, galaxies, and clusters arranged in an elegant pattern. This paradox chaos, giving birth to order, is a theme that resonates across many aspects of the cosmos. It's a reminder that sometimes the most profound structures arise from the most violent and unpredictable events. Philosophically, inflation challenges our understanding of time and space. In the blink of an eye, the universe was stretched to a scale we cannot fully imagine, and from that unimaginable growth emerged the universe we know today. It teaches us that the origins of order may lie in periods of intense disorder, and that the quiet, peaceful cosmos we observe is the result of extraordinary forces operating on scales beyond our comprehension. Inflation, in its paradoxical nature, invites us to rethink how we view the universe not as a static, predictable system, but as a dynamic, ever-changing process, driven by forces that are at once chaotic and exquisitely ordered. Eternal inflation and infinite pockets. The concept of inflation fundamentally reshapes our understanding of the universe. It suggests that the rapid expansion of the early universe was not just a one-time event, but could be an ongoing process, giving rise to multiple pockets of space, each with its own distinct laws and characteristics. This idea, known as eternal inflation, proposes that while our observable universe underwent a brief but extraordinary period of inflation, the process itself could continue indefinitely, creating an infinite number of disconnected regions, each of them evolving into a separate universe. What we see as our universe may merely be one bubble in an endless cosmic sea of others. Eternal inflation emerges from the same principles that drive the initial rapid expansion of space. During inflation, the energy field known as the inflaton causes space to expand exponentially. However, not all regions of space expand at the same rate. Some pockets of space may experience a cessation of inflation, while others continue inflating. These regions where inflation ends form what we call bubble universes. Each bubble has its own distinct properties with potentially different physical constants, laws of physics, and even dimension. Our universe, with its set of laws and constants, is just one of these bubbles, each isolated from the others by regions where inflation still reigns. The contrast between a single cosmos and a multiverse is both staggering and profound. A single cosmos implies that the entire universe, from its beginning to its end, is interconnected and governed by a single set of physical laws. In this scenario, everything within the universe is part of one cohesive whole, and the future can be predicted by understanding the present. The idea of a multiverse, however, shatters this coherence. It suggests that there is no single, unified universe, but rather an infinite number of universes, each with its own, potentially unique properties. These universes may never interact with one another, each existing in its own isolated bubble, separated by the endless expansion of space. Eternal inflation, by creating these disconnected regions, offers a solution to many mysteries in cosmology. For instance, it can help explain the apparent fine-tuning of the universe. In a multiverse scenario, each universe could have slightly different values for fundamental constants, such as the strength of gravity or the mass of elementary particles. While most of these universes may be inhospitable to life, our universe, with its perfectly tuned conditions, would be one of the lucky few where life could emerge. This anthropic principle suggests that the reason the universe seems so finely tuned for life is simply because we exist in one of the universes where those conditions are just right. Yet the idea of an infinite multiverse introduces its own set of philosophical questions. If there are countless other universes, each with its own set of physical laws, does this diminish the uniqueness of our universe? Are we just one of an infinite number of possibilities, insignificant in the grand scale of all existence? Does the existence of infinite versions of reality, where every possible outcome is realized, undermine the concept of meaning or purpose? Moreover, the multiverse theory also raises profound implications for the scientific method itself. If other universes are truly disconnected from ours, then they are fundamentally unobservable. We cannot travel to them, communicate with them, or even detect their existence directly. This leads to the dilemma of whether the multiverse is truly a scientific theory or more of a speculative philosophy, since it relies on the existence of realms that are beyond our observational reach. Yet, the multiverse also offers an inspiring possibility. It allows us to imagine that the universe is much larger and more varied than we ever thought possible. It speaks to the power of imagination in science and how far we are willing to stretch our understanding of reality. The idea of infinite pockets of space, each a self-contained cosmos, opens up a universe of possibility, filled with unseen worlds where the laws of nature could take forms we have yet to dream. Philosophically, eternal inflation and the concept of a multiverse remind us that the limits of our knowledge are not only shaped by the confines of space, but also by the boundaries of our imagination. If we are to fully embrace the true nature of the cosmos, we must not only look outward into the stars, but also look inward to challenge the assumptions we have about the fundamental structure of reality itself. The idea of an infinite multiverse pushes the limits of science and the very concept of what is knowable. Bubbles in the cosmic sea. Eternal inflation paints a picture of the cosmos as an ever-expanding sea, where each universe is a bubble inflating within a larger, infinite expanse. Imagine the universe we know as just one bubble in a frothy cosmic ocean, each bubble emerging from its own point of inflation, its own unique birth. These bubbles, each with potentially different physical laws, properties, and even dimensions, float in an endless sea of potential. What we call our universe is merely one such bubble, a brief, finite moment within an eternal, infinite process. The question arises, if each bubble universe exists independently, disconnected from the others, what does it mean for the nature of reality itself? Is the cosmos interconnected or isolated? The contrast between connectedness and isolation is at the heart of the bubble universe idea. Our universe, as we know it, feels inherently connected. Galaxies, stars, and even the fabric of space-time are bound together by gravity, electromagnetism, and other fundamental forces. The laws of physics seem universal and unified within the observable universe. However, in the framework of eternal inflation, the universe we observe is isolated, an island in a vast cosmic sea. Each bubble universe, like our own, could have completely different properties, governed by different physical constants or even different forms of reality. The regions beyond the cosmic horizon are invisible and inaccessible to us, suggesting a profound isolation between us and any other potential universes. In this model, the universe we experience is not a singular, unified entity, but one of many. These other universes, though they may emerge from the same cosmic process, are essentially isolated from ours. Their histories, their structure, their laws, everything is separate. The light from these other bubbles will never reach us, and their existence remains speculative, unobservable. The bubble universes are like distant islands in an ocean, floating far apart. Their existence inferred only through theory, not through direct evidence. Each is a self-contained universe, evolving on its own with no means of communicating with the others. Yet despite their isolation, there is a sense of connectedness in the concept of eternal inflation. The very process of inflation links all these universes together, connecting them through the same underlying mechanism, the same driving force. While each bubble might evolve independently, they are all part of the same cosmic process, generated by the same inflationary energy. In this way, even the most isolated bubble is connected to the others by the fabric of eternal inflation. The universes may be isolated in a physical sense, but in a deeper, fundamental sense, they share a cosmic origin. Philosophically, the idea of bubble universes raises questions about the nature of existence itself. Are we truly alone in our universe, or are there countless other worlds out there, beyond our reach, beyond our comprehension? Is the isolation of each universe a fundamental feature of existence, or merely a product of our limited perspective? If each bubble is self-contained, what does that say about the interconnectedness of all things? Are we part of a grand, unobservable unity, or are we merely one isolated island in an infinite sea of other possibilities? The notion of cosmic bubbles also challenges the way we think about life, meaning, and purpose. If our universe is just One bubble among many, how do we find significance in our existence? Are we merely a fluke of the universe's inflationary process, a random configuration of particles in one of countless bubbles, or is there something unique, something precious, about our experience of the cosmos, about the interconnectedness we feel with the universe we observe? These questions, unanswered, remain the very heart of the mystery of our place in the cosmos. Thus, while the bubble universe theory suggests profound isolation on a cosmic scale, it also offers a surprising sense of unity, connecting all bubble universes through the shared process of eternal inflation. In the vast, infinite expanse of the cosmos, each bubble is isolated, but together they form a broader cosmic tapestry that reminds us of the vastness of existence, an existence that is both deeply isolated and fundamentally interconnected. Different physics, different realities. In the realm of theoretical physics, string theory proposes a landscape of possibilities so vast that it challenges the very idea of a single, unified set of laws governing the universe. According to string theory, the fundamental particles we observe are not points, but tiny vibrating strings, and the laws of physics arise from the different ways these strings can vibrate. But here's where it gets astonishing. The vibrational patterns could correspond to an enormous variety of possible universes, each with its own distinct set of physical laws. This landscape of solutions, often referred to as the string landscape, presents us with a radically different view of the cosmos. Not just one universe with one set of laws, but a multiverse of realities where the fundamental principles of physics may differ from one region to another. The contrast between universality and plurality in this context is profound. Traditionally, science has operated under the assumption that the laws of physics are universal, that they apply throughout the entire universe, regardless of location or time. Gravity, electromagnetism, the strong and weak nuclear forces, the speed of light, all of these are constants that we assume hold true everywhere. This universality has been one of the cornerstones of scientific progress. We can predict the behavior of distant stars, the structure of atoms, and the motion of planets based on these shared principles. The universe, as we know it, seems to function as a coherent, unified system. However, the string landscape suggests that this coherence might be an illusion. Rather than a single, universal set of laws, the cosmos may be composed of an almost infinite number of universes, each with its own distinct physical laws. The constants of nature, such as the strength of gravity, the mass of the electron, or the cosmological constant, could vary from one universe to another. In some regions, gravity could be stronger, in others weaker. Some universes might lack certain forces altogether, while others could have completely new ones. If this is true, our universe with its familiar laws would be just one possible manifestation of the underlying principles of string theory, a tiny slice of an infinitely diverse multiverse. This idea is not just speculative, it arises naturally from the equations of string theory. The landscape itself is vast, comprising a huge number of potential solutions to the equations governing the theory, each corresponding to a different set of physical laws. Estimates suggest that there may be on the order of 10 to 510, 500 per 500 different possible solutions, each defining a different universe with its own distinct laws. In some of these universes, conditions could be radically different, even hostile to life as we know it. In others, they might be perfectly suited to the emergence of life. The vast variety of potential universes within the string landscape thus opens up the possibility of infinite variety in the very structure of reality itself. Yet as awe-inspiring as this plurality is, it comes at a cost. The notion of an infinite variety of laws challenges the very foundation of scientific inquiry. If the laws of physics can vary so wildly from one universe to another, how can we ever hope to make definitive statements about what the true nature of reality is? If every possible configuration is realized somewhere in the landscape, does this diminish the quest for universal laws? Does the existence of so many possibilities make our own universe less special, less unique, if it is just one outcome among countless others? Philosophically, this plurality forces us to confront the tension between our desire for order and our recognition of chaos. For millennia, humans have sought a unified theory of everything, a single set of principles that explains the nature of the cosmos. The pursuit of this ultimate explanation has driven scientific exploration, from Newton's laws of motion to Einstein's theory of relativity and beyond. But the string landscape implies that this search for universality may be misguided, at least on a cosmic scale. The universe, it seems, may not have a single set of governing laws. Instead, it may be composed of an infinite variety of realities, each with its own distinct rules, governed by the underlying strings. At the same time, the very idea of a multiverse populated by many different sets of laws invites a new kind of awe. In a universe governed by string theory's landscape, the very concept of reality expands beyond the limits of imagination. No longer do we face the confines of a single set of rules, but an infinite array of possibilities, each offering different pathways for the evolution of matter, energy, and even life itself. This cosmic plurality stretches the boundaries of what we understand as possible, forcing us to reconsider the nature of the universe itself and our place within it. Thus, the tension between universality and plurality in string theory is not just a scientific dilemma, but a philosophical one. As we look out at the cosmos, we may realize that the very laws that govern our existence could be part of a much larger, more diverse cosmic tapestry, one where our universe is not the only reality, but just one among a staggering multitude, each shaped by its own distinct set of laws. Collisions across the divide. What if, in the vast expanse of the multiverse, universes occasionally brush against one another? What if the boundaries between bubbles regions of eternal inflation are not as isolated as we thought? The concept of universes colliding or interacting in some way is a speculative idea that tantalizes the imagination and raises profound questions about the nature of space, time, and reality itself. While the notion of bubble universes suggests isolated regions, could there be evidence of these cosmic collisions? Could the ripples of their contact be imprinted in our universe, leaving traces that we might one day detect? The idea of universes brushing against ours might sound like science fiction, but it's rooted in theoretical possibilities, in the framework of eternal inflation, where inflationary pockets of space give birth to bubble universes. The rapid expansion of space could cause these bubbles to eventually collide. Such collisions might produce observable effects disturbances in the cosmic microwave background, CMB radiation, peculiarities in galaxy formation, or anomalies in the distribution of dark matter. While these events are likely to be rare and their effects faint, the very possibility of detecting a collision between universes pushes the boundaries of what we understand about the cosmos. The signature of such a collision might not look like a typical explosion or impact. Instead, it would be subtle, perhaps a slight anomaly in the CMB, which is the remnant radiation from the Big Bang. If a bubble universe collided with ours, the shockwave from that event might have left imprints on the fabric of space-time, distorting the CMB in a unique way. These distortions could appear as cold or hot spots in the CMB areas where the temperature of the radiation deviates from the expected pattern. They would not be easy to detect, but advanced cosmological surveys and more sensitive instruments might one day provide us with clues to this cosmic interaction. Another potential consequence of such collisions could be the creation of new structures in the universe. The violent encounter of two bubble universes could, in theory, lead to the formation of cosmic features, unexpected galaxy formations, or black hole mergers that defy our current models. These events might be rare, but they could leave observable traces in the distribution of galaxies or the clustering of dark matter, phenomena that we are just beginning to study on a large scale. Philosophically, the idea of universes brushing against one another raises profound questions about the nature of reality. If such collisions are possible, they suggest a universe far stranger than we've imagined, one that is not merely isolated and self-contained, but interconnected with others. It opens up the possibility that our universe, our reality, is not a solitary existence, but part of a vast cosmic network of universes, each with its own laws and histories, occasionally interacting in ways we cannot yet fully comprehend. Moreover, the idea of collisions across the divide forces us to confront the limits of our knowledge. If we are able to detect evidence of such interactions, it would fundamentally challenge our understanding of space, time, and causality. It would blur the lines between what we consider our universe and the larger, possibly infinite multiverse. The discovery of such evidence would not only reveal the presence of other universes, but also suggest that reality, as we understand it, is far more intricate and interconnected than we ever imagined. Ultimately, the possibility of universes brushing against ours invites us to think beyond the conventional boundaries of space and time. It suggests that our universe is not an isolated entity, but part of a greater cosmic tapestry, a constantly evolving interplay of multiple realities, each capable of interacting in ways we are only beginning to imagine. CMB anomalies. The cosmic microwave background, CMB, is often described as the afterglow of the Big Bang, the faint radiation left over from the birth of the universe, approximately 380,000 years after the Big Bang itself. This radiation is remarkably uniform, with only tiny fluctuations in temperature across the sky, fluctuations that correspond to the seeds of structure in the universe, where gravity eventually pulled matter together to form stars, galaxies, and clusters. Yet within this sea of near-perfect uniformity, there are anomalies, oddities that seem out of place and have intrigued scientists for decades. These include cold spots and unexpected alignments, features that some suggest could hint at something far stranger than mere cosmic noise. Could these anomalies be signals from beyond our universe? Or are they simply statistical flukes, noise? In the data that we have yet to explain, the cold spots in the CMB are perhaps the most famous of these anomalies. These areas of the sky appear significantly cooler than the surrounding regions, suggesting something out of the ordinary. One of the most notable of these is the cold spot, a large region that is roughly 1.8 degrees Celsius colder than its surroundings. The spot's size and temperature contrast seem too large to be explained by conventional cosmic fluctuations. Some theorists have speculated that this cold region could be the result of a collision between our universe and another bubble universe in the multiverse. If this cold spot is indeed a remnant of such an event, it could represent the first direct evidence of a universe brushing against ours, a rare and profound glimpse into the nature of the multiverse itself. The alignments in the CMB are another set of puzzling features. The CMB is expected to be isotropic, that is, it should look the same in all directions. However, some studies have found small, unexpected alignments in the temperature fluctuation, suggesting that the large-scale structure of the CMB might be oriented in ways that we don't fully understand. These alignments could be a signal of some underlying structure or influence affecting the universe on a cosmic scale. Some have even proposed that this alignment could point to a preferred direction in space, an indication of some fundamental, unexplained property of the universe. Is it a sign of a deeper order, or is it simply a statistical anomaly that will fade with further observation? The fundamental question, of course, is whether these anomalies are signals or noise. In the world of physics, distinguishing between the two is often the hardest part. Noise is any random fluctuation that doesn't carry any meaningful information. Signals, on the other hand, are patterns that persist across repeated observations and are usually interpreted as carrying some deeper meaning or message. In the case of the CMB, noise could be caused by imperfections in our instruments, errors in data processing, or even unknown astrophysical phenomena. Signals, however, suggest a more profound revelation, a pattern that persists and tells us something we don't already know about the universe. The debate between signal and noise is crucial in cosmology. A false signal could mislead researchers into developing theories that aren't actually supported by reality. On the other hand, dismissing an actual signal as mere noise would mean missing out on an incredible discovery. The cold spots and alignments in the CMB are certainly intriguing, but they require more than just a passing glance. They demand rigorous investigation, careful analysis, and a deeper understanding of the cosmic processes that could have caused them. Could they be the echoes of an encounter between universes, the remnants of a collision between bubbles in the multiverse? Or are they the result of some as yet unknown astrophysical phenomenon that is merely playing tricks on our observations? Philosophically, the possibility that these anomalies could be signals from beyond our universe challenges the very nature of reality. What does it mean if we are able to detect the influence of other universes or even remnants of their existence? It forces us to reconsider our place in the cosmos, not as isolated observers of a singular reality, but as participants in a much larger and more interconnected multiverse, one whose boundaries we have only begun to comprehend. In the end, the cold spots and alignments in the CMB are more than just puzzles. They are gateways to a deeper understanding of the universe and its possible connections to other realms. Whether they are signals or noise, they remind us that the universe is not just a static backdrop to our lives, but a dynamic, ever-changing expanse filled with mysteries that have yet to be unraveled. The skeptic's case, the concept of the multiverse, an infinite array of universes, each with its own set of physical laws, has captivated the imagination of both scientists and the public alike. From the peculiarities of quantum mechanics to the cosmological implications of eternal inflation, the idea of a multiverse offers an elegant solution to many unresolved questions in physics. But despite its theoretical allure, there is a significant faction of the scientific community that remains deeply skeptical of the multiverse hypothesis. The central objection? The multiverse, as currently proposed, is inherently untestable and, therefore, unscientific. One of the core principles of science is that a theory must be testable, able to make predictions that can be verified or falsified through observation or experimentation. This is what distinguishes science from philosophy or metaphysics. For instance, the theory of evolution provides predictions that can be tested through fossil records and genetic analysis. The theory of relativity makes predictions about the bending of light in gravitational fields, predictions that have been confirmed by observation. But the multiverse, in its current form, does not lend itself to direct testing. If there are multiple universes, each existing in its own bubble, then by definition, they are beyond our observational reach. Light, or any form of information, cannot travel between universes, and thus we have no way of directly detecting or interacting with them. This presents a fundamental challenge. How can a theory be considered scientific if it cannot be tested or observed in any meaningful way? Critics argue that the multiverse hypothesis, like many ideas in theoretical physics, is more philosophy than science. In their view, it's an elegant mathematical extrapolation, but it lacks empirical support. They point out that the multiverse theory is often invoked to explain the fine-tuning of the universe. The anthropic principle, which suggests that the physical constants of our universe are precisely set to allow life, is used to argue that our universe is simply one of many, where in some, the conditions are not conducive to life. However, this reasoning doesn't offer a testable hypothesis. Instead, it provides an explanation for why our universe seems perfectly suited for life by suggesting that there are countless other universes, some with different conditions, but offering no way to observe or verify this claim. Moreover, some skeptics believe that invoking the multiverse as an explanation for the universe's fine-tuning raises more questions than it answers. If there are infinite universes with random physical laws, why are we seeing a universe that is so finely tuned for life, and why should we assume that a multiverse exists in the first place, especially when it seems to make no difference to our observable universe? To critics, this idea risks turning into an intellectual cop-out, where the multiverse is used to explain away any phenomenon that seems difficult to account for within the framework of our known universe, without offering real insight into the fundamental nature of reality. Another key objection lies in the multiverse's lack of explanatory power. While the theory can offer potential solutions to certain cosmological puzzles, such as the fine-tuning problem, it does so by introducing an untestable, unfalsifiable premise. This makes it difficult to determine whether the multiverse hypothesis is genuinely contributing to our understanding of physics or merely providing a catch-all explanation for the mysteries that remain unsolved. In essence, critics argue the multiverse is a theory in search of evidence, rather than a theory that arises from evidence. Skeptics also raise concerns about the implications of accepting a multiverse as a scientific theory. They fear that embracing untestable ideas might lead to a slippery slope where any theoretical concept can be deemed valid simply because it fits into a mathematical framework, regardless of whether it can be observed or tested. This would undermine the very principles of science, which rely on empirical validation. The danger, according to skeptics, is that science could become mired in speculative ideas with no grounding in reality, diluting its power to uncover the true nature of the universe. In addition to these scientific concerns, there is a deeper philosophical critique of the multiverse idea. If the existence of multiple universes is fundamentally untestable, then it might be more accurate to categorize it not as a scientific theory, but as a metaphysical hypothesis. While metaphysical ideas can be intellectually stimulating, they are not bound by the rigorous standards of scientific inquiry. Critics argue that science should focus on theories that can be empirically tested, rather than ideas that exist solely in the realm of speculation. Ultimately, the skeptic's case against the multiverse is not a rejection of its potential to explain certain aspects of cosmology, but a cautionary call to hold theories to the standards of scientific inquiry. Until the multiverse hypothesis can make predictions that can be tested and observed, it remains, for many, an interesting but ultimately unscientific idea, one that, for now, resides in the realm of speculative philosophy rather than physics. The limits of knowing. In the pursuit of knowledge, there comes a moment when we are confronted not by the lack of information, but by the inherent limits of what can be known. The boundaries of human understanding are not just a result of insufficient data or technology, but are shaped by the very nature of reality itself. This concept, epistemic boundaries, poses a fundamental challenge to our search for truth. How far can our minds stretch to comprehend the cosmos? Is there an ultimate limit to knowledge, or can we, in theory, grasp the entirety of existence? Throughout history, humans have sought to transcend these boundaries. We have gazed at the stars, split atoms, and peered into the deepest recesses of the universe with increasingly sophisticated instruments. Every step forward in science brings with it the tantalizing possibility that we can uncover every secret of the universe. Yet with each discovery, we are reminded that there are questions we cannot answer, limits we cannot overcome, and mysteries we cannot solve. One of the key aspects of epistemic boundaries is the concept of unknowability. Some phenomena may be beyond our capacity to understand, not because we lack the proper tools, but because they are fundamentally inaccessible to human cognition. The idea that the universe could contain realms or truths beyond our grasp, whether due to physical constraints or the very nature of consciousness, forces us to confront the humbling possibility that some aspects of reality will always remain hidden. We are, in this sense, bound by the limits of our perception, our senses, and the cognitive structures that allow us to make sense of the world. In cosmology, this question arises with the notion of the cosmic horizon, the boundary beyond, which we can never observe or gain information. As space expands and galaxies drift farther away, there will be regions of the universe that are forever out of our reach, their light unable to ever reach us. This is not just a matter of technology or time, it is a fundamental limit imposed by the structure of the cosmos. We may be able to measure the expansion of the universe and infer certain properties about the regions beyond the horizon, but the information will always remain incomplete, forever beyond our observational grasp. This boundary reminds us that no matter how advanced our science becomes, there will always be aspects of the universe that elude us. Philosophically, the existence of epistemic boundaries forces us to reconsider our understanding of knowledge itself. We tend to view knowledge as a linear progression, a journey toward ever greater understanding. But what if this journey is not a straight line, but a spiral, one that takes us closer to some truths, while forever leaving others just out of reach? What if, in the quest for absolute understanding, we come to realize that the most profound truths are not those that can be measured or explained, but those that remind us of the limits of our knowledge? The contemplation of epistemic boundaries also highlights the tension between humility and ambition in our intellectual pursuits. We are naturally driven to seek answers, to push against the frontiers of knowledge, and to conquer the unknown. But this drive often comes with a blind spot, the failure to recognize that some questions may never be answered, some horizons may never be crossed. Accepting this can be liberating, allowing us to appreciate the beauty and wonder of the universe, not because we understand it fully, but because we realize the limits of understanding itself. Ultimately, the limits of knowing invite a kind of wisdom, the wisdom of accepting that knowledge is not just about uncovering truths, but about embracing the mysteries that remain. The search for knowledge in this sense is not a race to conquer the unknown, but a journey that teaches us to appreciate the unknown itself. In the vastness of the universe, there will always be questions without answers, and that is perhaps the greatest mystery of all, ancient myths of beyond. Throughout human history, the edges of the world have captured our imagination. In ancient cosmologies, the limits of the known universe were often defined not by physics or mathematics, but by myth, symbol, and story. From the domed heavens to the endless waters, ancient cultures created maps of the cosmos that were both practical and profoundly spiritual. These maps, though symbolic, reflected humanity's need to understand its place in the universe and the nature of the boundaries that defined the known and unknown. Today, modern science has replaced these mythical boundaries with a more precise but still elusive understanding of the cosmos. The question remains, how do ancient conceptions of the universe compare to our own? In ancient times, the edge of the world was often conceived as a literal, physical boundary. The Babylonians envisioned the Earth as a flat disk surrounded by a vast primordial ocean. To them, the cosmos was not a space expanding outward, but a static, enclosed system with the heavens above and the underworld below. In such a cosmology, the edge of the world was not just a limit to be explored, it was a boundary that separated the known from the unknown, the divine from the mortal. The ancient Greeks, meanwhile, imagined the cosmos as a series of concentric spheres. For Ptolemy, the Earth was at the center, surrounded by the orbits of the moon, planets, and stars, all contained within a great celestial dome. The outermost sphere, the prime mover, was believed to be a realm of perfection, untouched by the imperfections of the material world. This celestial dome was the ultimate edge of the known universe, beyond which lay the realm of the divine. In this view, the boundaries of the universe were not defined by a physical edge, but by a metaphysical one, the transition from the earthly to the divine. These ancient cosmologies offered a tangible sense of limits, a way to understand the vastness of the universe in terms of human experience. The edges of the world were places of mystery and awe, inhabited by gods, monsters, or spirit. The journey beyond these boundaries was a perilous one, undertaken by mythic heroes or gods. For instance, in Mesopotamian myth, the hero Gilgamesh embarks on a journey to the edge of the world to seek immortality, encountering monstrous creatures and cosmic forces that remind him of humanity's limitations. In Greek mythology, the edge of the world was also a place of great peril, often linked to the ocean or the realm of the dead. Contrast this with the modern scientific view, where the edges of the universe are defined not by myth or imagination, but by the limits of observation. The observable universe is bounded by the speed of light and the finite time since the Big Bang. Beyond that lies the cosmic horizon, an edge that is not a literal boundary, but the limit of what we can see and measure. Modern cosmology tells us that the universe is expanding, and the edges of the universe are not fixed, but recede from us as space itself stretches. This edge is not a place of gods or mythic beings, but a fundamental feature of the universe's structure, one that might be defined by the unknown nature of dark energy and the accelerating expansion of space. While ancient maps of the cosmos were framed by human experience and imagination, they were also filled with profound meaning. Today, we map the universe using the tools of science telescopes, satellites, and mathematical models. Yet, the ancient impulse to define the limits of the known universe endures. It reflects a universal need to understand where the known world ends and the unknown begins. Whether in the form of domed heavens, oceans, or the expanding cosmic horizon, humans have always sought to chart the boundaries of existence. In the end, the ancient maps of the cosmos, while mythic and poetic, were attempts to grapple with the same questions that drive modern science. What lies beyond the known world? How far does the universe stretch? And what does it mean for us to exist at the edge of something so vast and mysterious? While the tools and frameworks have changed, the fundamental human quest to explore the limits of reality remains the same. The myths may have given way to science, but the longing to understand the beyond endures. Infinity is a concept that stirs both awe and existential dread. It embodies the ultimate paradox. It is simultaneously a source of profound comfort and a deep well of unease. To contemplate infinity is to grasp at the limitless, the boundless, the eternal, but also to confront the terrifying realization that nothing is finite. Nothing has an end. For millennia, humans have sought to understand infinity, to make it comprehensible, and to reconcile it with our limited, finite existence. Yet, in many ways, infinity remains a concept that escapes our full understanding, a symbol of both our greatest aspirations and our deepest anxieties. On one hand, infinity can be comforting. It suggests a universe that stretches beyond the confines of our daily lives, one that is vast, eternal, and filled with possibility. In the infinite, there is no end to knowledge, no limit to the number of stars, galaxies, or worlds waiting to be discovered. The infinite universe is a playground for the curious mind, an invitation to explore, to venture ever farther into the unknown. Infinity also offers a kind of cosmic assurance that no matter how small we may feel, we are part of something that transcends the boundaries of our individual lives. We are not mere fleeting moments in time, but particles of a larger, ongoing process that stretches back to the beginning of time itself and continues onward for eternity. In this way, infinity offers solace, a reassurance that existence is not just finite or temporary, but part of an endless unfolding. The idea that the universe has no end means that our search for meaning, knowledge, and understanding has no final conclusion. We are not bound by limits, but propelled by them. In the face of personal mortality, the idea of an infinite cosmos can provide comfort, reminding us that while our lives may be brief, the universe itself will endure. The idea of infinity frees us from the constraints of time, encouraging us to dream big, to imagine possibilities beyond the constraints of the here and now. But this same infinity also holds a darker, more unsettling power. If the universe stretches without end, then everything becomes small in comparison. The infinite vastness can make us feel insignificant, lost in the immensity of time and space. We are mere specks floating in a cosmos that stretches far beyond our comprehension, where our actions, no matter how meaningful they may seem in the moment, are but fleeting shadows in the grand scheme of things. This realization that our lives may be inconsequential in the face of infinity can stir deep existential dread. It is the terror of realizing that the universe does not care about our individual stories, that the vastness of time renders our struggles and triumphs meaningless. In the grand calculus of eternity, the thought of infinity can also challenge our sense of purpose. If the universe is infinite, is there any ultimate meaning to our existence, or is it just an accident in an endless chain of events? The infinite scope of the cosmos can be overwhelming, pushing us to question our place within it. If the universe never ends, will there ever be a moment of closure? Will there ever be an ultimate answer to the questions we ask? Or are we condemned to an eternity of seeking with no final destination, no conclusion to our search for meaning? In philosophical terms, infinity represents both the ultimate possibility and the ultimate limitation. It is the horizon that we can never cross, the boundless ocean that we are forever swimming in but can never escape. It reminds us of our human fragility and impermanence, forcing us to reckon with the uncomfortable fact that we may never fully understand the true nature of existence. Our minds, finite as they are ill-equipped to grasp infinity in its entirety. It stretches beyond the bounds of logic, beyond the limits of time and space, and leaves us with a sense of awe and terror that we can neither escape nor fully comprehend. Yet in the tension between comfort and terror, there lies something deeply human. To confront infinity is to confront the core of existence itself, the endless search for meaning, the unquenchable thirst for understanding, and the existential realization that we are both part of something infinitely greater than ourselves and forever isolated in our own fleeting lives. Infinity pushes us to dream and to despair, to seek and to question, to find solace in the vastness and fear in the emptiness. In the end, infinity represents both the grandeur and the futility of human thought. It offers boundless potential and exposes the limits of our comprehension. The infinite, in its paradoxical nature, reminds us of both our place in the cosmos and our inability to fully grasp the cosmos itself. It is the ultimate mystery, a challenge that will forever exist at the heart of our curiosity, our search for meaning, and our confrontation with the unknown. The mirror of our imagination. The idea of beyond, whether it refers to the edge of the universe, the boundaries of human knowledge, or the limits of existence, serves as both a destination and a mirror. As we contemplate what lies beyond, we are not just pondering the vast cosmos, but also reflecting on our own nature. The unknown becomes a canvas upon which we project our deepest hopes, fears, and aspiration. The beyond is not just an external mystery. It is an inward journey that tells us as much about who we are as it does about the universe itself. Humans have always looked toward the horizon, both literally and figuratively. Whether it's the edge of the Earth, the farthest reaches of space, or the boundaries of time itself, we are driven by a need to explore. This drive to seek the unknown reveals much about the essence of our species. We are curious, restless, and ambitious creatures, constantly reaching for more, always wondering what lies just out of sight. In this sense, the beyond is not just a feature of the cosmos, but a reflection of our own inner world, our yearning for meaning, our desire for understanding, and our existential need to transcend the limits of our finite existence. In contemplating the vastness of space or the infinite reaches of time, we confront not only the scale of the universe, but the limits of our own minds. The cosmos, with all its complexity and mystery, pushes us to reflect on our place in the universe. Are we insignificant specks in an infinite void, or do we hold a unique position in the grand scheme of things? Our thoughts about the beyond often reveal our own deepest concerns about mortality, purpose, and meaning. We seek answers to these questions in the stars, as though the universe might somehow reflect the answers we seek about our own lives. The beyond also reflects our fear of the unknown. In ancient times, the edges of the earth were filled with myths of monsters, gods, and dangers. Today, the boundaries of the universe are filled with similar fears that we may never understand the true nature of existence, or that our place in the cosmos is ultimately meaningless. Yet these fears are not merely a response to the vast emptiness of space, but also a reflection of our own existential anxieties. The cosmos, in all its immensity, becomes a symbol of the unknown aspects of ourselves, those parts of our psyche that we cannot fully comprehend or control. In seeking to understand the universe, we may also be seeking to understand the deepest parts of our own consciousness. At the same time, the beyond symbolizes our potential for growth and discovery, the drive to explore the unknown, to push the boundaries of human understanding is one of our most profound qualities. The beyond is not just a place of mystery and fear, but a realm of infinite possibility. Each new discovery, each new step forward in science opens up new horizons and expands our sense of what is possible. The universe, in this sense, becomes a reflection of our own potential, our ability to learn, to adapt, and to overcome the challenges that lie before us. By gazing outward, we are reminded of our inner capacity for growth, for exploration, and for transformation. Ultimately, the idea of the beyond is inseparable from our own identity as explorers, dreamers, and seekers. It tells us as much about the human condition as it does about the cosmos. The universe, with all its mystery and awe, serves as a mirror reflecting our own hopes, fears, and desires. The questions we ask about the beyond, the questions about the nature of existence, the purpose of life, and the ultimate fate of the universe are, in many ways, the same questions we ask about ourselves. And in this search for the unknown, we are not just uncovering the secrets of the cosmos, but also discovering more about who we are, what we seek, and what we might yet become. Next generation telescopes. As our understanding of the universe deepens, so too does our ability to look further, peer deeper, into the vast expanse of space, and uncover the mysteries that lie beyond our reach. The advent of next-generation telescopes, such as the James Webb Space Telescope, JWST, Euclid, and Roman, promises to revolutionize our view of the cosmos, offering glimpses into regions of space and time previously beyond our observational capabilities. These powerful instruments aim to push the boundaries of human knowledge, allowing us to explore distant galaxies, study the formation of stars, and probe the dark corners of the universe, including the elusive phenomena of dark matter and dark energy. Yet, as with all technological advancements, these telescopes also reveal the delicate tension between detail and limitation, how far we can look, and what we might never see. The JWST, launched in December 2021, is perhaps the most ambitious space observatory ever built. Designed to be the successor to the Hubble Space Telescope, JWST's primary focus is infrared astronomy, allowing it to look through cosmic dust clouds and observe distant galaxies that have been hidden from view. Its large, segmented mirror and advanced infrared detectors enable it to peer back to the very early universe, examining the first stars and galaxies that formed after the Big Bang. By observing galaxies as they were billions of years ago, JWST will provide insights into the processes that shaped the universe in its infancy. Yet, even with its unprecedented power, JWST's ability to see beyond certain limits is still constrained by factors such as the speed of light, the expansion of space, and the vast distances between objects. The Euclid mission, launched in 2022, takes a different approach, focusing on the mysteries of dark matter and dark energy. By mapping the geometry of the universe with high precision, Euclid aims to uncover the hidden structure of space-time and provide answers to some of the most profound questions in cosmology. By studying how light from distant galaxies is bent by the gravitational effects of unseen dark matter, Euclid seeks to illuminate the nature of these mysterious forces that make up the vast majority of the universe's mass and energy. While its insights could reshape our understanding of the cosmos, it too is limited by the precision of its instruments and the complexity of the phenomena it studies. The very nature of dark energy and dark matter remains elusive, and Euclid's mission is only a step toward unraveling those cosmic mysteries. The Roman Space Telescope, expected to launch in the mid-2020s, will build upon the work of JWST and Euclid. Named after the pioneering astronomer Nancy Grace Roman, this telescope will focus on a broad range of astronomical phenomena, including exoplanets, star formation, and the geometry of the universe. One of Roman's key missions is to study the expansion of the universe and the role of dark energy in driving its acceleration. Roman will also assist in the search for exoplanets, particularly those that are similar to Earth, and study their atmospheres to assess their potential for habitability. Roman will provide us with incredibly detailed views of distant stars and galaxies, but even its vast capabilities cannot escape the limitations inherent in observing the universe on such an expansive scale. Its observations will be limited by the same challenges faced by all telescopes primarily: the limits of resolution, sensitivity, and the vast distances separating objects. The contrast between the level of detail these next-generation telescopes can provide and the limitations they face is profound. On the one hand, these instruments represent humanity's greatest leap in observational technology, capable of detecting and analyzing faint signals from the farthest reaches of the cosmos. They allow us to study the universe in unprecedented detail, revealing galaxies that formed just a few 100 million years after the Big Bang, capturing the birth and death of stars and unveiling the influence of dark matter in shaping the universe's structure. On the other hand, they also remind us of the inherent limitations in our ability to observe the universe. No matter how powerful these telescopes become, they are still bound by the speed of light, the finite time since the Big Bang, and the accelerating expansion of space. There will always be regions of the universe that remain beyond our reach, their light forever stretched beyond detection. These limitations are not merely obstacles, they are reminders of the vastness of the cosmos and the humility required in our search for understanding. The more we discover, the more we realize how much remains hidden, how much of the universe lies just out of sight, beyond the grasp of even our most advanced instruments. Yet, it is in this very tension between what we can see and what we can never fully know that the true beauty of exploration lies. The next generation telescopes will not just reveal the universe in greater detail, they will also illuminate the boundaries of our understanding, challenging us to look beyond the visible and confront the unknown with awe and curiosity. Cosmic messages. In the quest to understand the cosmos, we've relied primarily on light, visible, infrared, ultraviolet, and X-rays to decode the mysteries of the universe. Light, or electromagnetic radiation, has long been our primary messenger from the stars, galaxies, and distant realms of space. But light has limitations. It can only carry so much information, and in many cases it struggles to penetrate the densest cosmic phenomena such as black holes or the dense clouds of gas and dust that obscure our view. To reach beyond these limitations, scientists have turned to other messengers: neutrinos and gravitational waves, particles and ripples that offer a glimpse into the universe's most hidden, most violent, and most distant events. These cosmic messengers promise to unlock new ways of observing the universe, allowing us to probe regions and phenomena that light alone cannot reveal. Neutrinos, often referred to as ghost particles, are subatomic particles that interact very weakly with matter. In fact, neutrinos can pass through entire planets without ever being detected or interacting with any atoms. This remarkable property makes them both elusive and powerful as probes of the universe's most extreme environment. Neutrinos are produced in vast quantities by some of the universe's most energetic processes: supernova, the collision of black holes, and the fusion reactions within the cores of stars. They carry information about the very processes happening deep inside these phenomena, allowing us to learn about objects that we could otherwise never observe directly. The ability to detect neutrinos from distant supernovae, for example, gives us a unique glimpse into stellar explosions that would otherwise be hidden. When a massive star collapses and explodes in a supernova, it emits an enormous burst of energy, but only a fraction of this energy comes in the form of light. The majority of it is released as neutrinos. These neutrinos can travel through space without being absorbed or scattered, arriving at Earth long before the light from the explosion. By studying the neutrinos emitted in a supernova, scientists can better understand the mechanisms behind these catastrophic events, which are thought to play a crucial role in the creation of heavy elements and the formation of black holes. In this sense, neutrinos are a time capsule, providing us with crucial information about stellar life cycles and the underlying physics that governs them. Gravitational waves, on the other hand, offer an entirely different way of probing the universe. Predicted by Albert Einstein in 1915 as part of his theory of general relativity, gravitational waves are ripples in spacetime itself, caused by the acceleration of massive objects. When two black holes merge, for example, they send out gravitational waves that propagate through space, stretching and squeezing the fabric of spacetime as they travel. These waves carry information about the masses, spins, and behaviors of the objects involved, providing insights into the nature of black holes, neutron stars, and other exotic cosmic phenomena. Gravitational waves are a direct probe of space-time, unlike light, which is affected by the medium it passes through. This means that gravitational waves offer a unique and unobstructed view of the universe's most extreme phenomena. The detection of gravitational waves by the LIGO, Laser Interferometer, Gravitational Wave Observatory, and Virgo collaborations in 2015 opened a new window onto the universe. These detections, which confirmed Einstein's century-old prediction, revealed the merger of two black holes in a distant galaxy, an event that had been invisible to traditional telescopes. Since then, gravitational wave astronomy has provided numerous breakthroughs, including the detection of neutron star mergers, which provide key insights into the formation of heavy elements like gold and platinum. However, while neutrinos and gravitational waves open new avenues for exploration, they are also fraught with their own challenges. Neutrinos are difficult to detect because of their weak interactions with matter, requiring massive, sensitive detectors, often buried deep underground, to shield them from other particles. Gravitational waves are similarly elusive, requiring incredibly precise measurements of spacetime distortions. The detectors used to capture these waves are so sensitive that they must be isolated from even the tiniest vibrations, making their construction and maintenance an immense technical challenge. Despite these obstacles, the pursuit of these cosmic messengers is pushing the boundaries of science, offering us unprecedented access to the inner workings of the universe. While light has been our primary tool for understanding the cosmos, neutrinos and gravitational waves provide us with new perspectives, offering us the chance to observe and study phenomena that have previously been hidden from our gaze. They allow us to peer into the darkest corners of space, into the heart of black holes, the aftermath of cosmic collisions, and the birth and death of stars. In a broader sense, the study of these cosmic messengers challenges our very notion of observation. We are forced to recognize that there are many ways to see the universe, many forms of information that do not rely on light. As we develop the technology to detect and interpret these signals, we expand our ability to understand the universe not just through the lens of visible radiation, but through the entire spectrum of cosmic phenomena. Neutrinos and gravitational waves, like whispers from the depths of space, offer us an invitation to explore the universe in ways that once seemed impossible, pushing the boundaries of what we can know. The endless mirror, the concept of infinity, stirs a paradox within the human mind, especially when we turn it toward the nature of existence itself. Imagine for a moment an infinite repetition of everything, the idea that every event, every action, every thought, and every moment in our lives is not a singular experience, but part of an endless cycle, eternally recurring in a cosmic loop. This notion, known as eternal recurrence, suggests that the universe, in its infinite vastness, repeats itself in an endless dance. Each instance of time, from the most mundane to the most profound, echoes endlessly like an infinite mirror reflecting a single moment over and over again. In this view, nothing is truly new. Every star that rises, every galaxy that forms, every human born, these are not unique events, but part of an eternal cycle that repeats ad infinitum. The landscapes of our lives, the choices we make, the triumphs and failures, these will occur again in precisely the same way infinitely. The repetition is not random but exact. The universe's laws, the forces of nature, the constants that define reality, everything that shapes existence will repeat, as if the cosmos is locked in a loop that cannot break. And perhaps most unsettling of all, it is not just the grand Events that repeat, but the quiet, intimate moments as well, the feeling of a sunset on your face, the sound of your own laughter, the quiet of a morning walk. All these will recur endlessly, as if we are each trapped in a cycle we cannot escape. This vision of infinite repetition has profound implications for our understanding of existence and meaning. At first, it can feel like an unsettling thought. The idea that everything, no matter how significant, might be bound to repeat endlessly can drain life of its uniqueness. If every moment, every experience is destined to recur infinitely, then what is the value of choice, of action, of change? Are we simply playing out a script, acting out roles that have already been written, destined to unfold in precisely the same way? Yet there is a strange comfort in this vision too, for in a universe that repeats infinitely, everything that has ever been or ever will be is given eternal significance. Every moment, no matter how fleeting, will return. There is something oddly reassuring about the thought that every feeling, every connection, every joy or sorrow will resurface in the grand cycle of time. The small, seemingly insignificant moments of life, those passing interactions with strangers, those quiet moments of reflection, are not lost in the sweep of history, but preserved, eternally woven into the fabric of the cosmos. They are part of the great cosmic dance, repeating in infinite variations forever. In this sense, the infinite repetition of all things offers a strange immortality to our lives, a sense that nothing is ever truly gone, but will always return in some form. However, as we contemplate this eternal recurrence, it also raises questions about free will, fate, and the nature of time itself. If everything repeats, do we have agency, or are we merely puppets in an infinite cosmic play? Are our actions truly our own, or are they simply preordained to repeat in the same pattern? The question of whether we live freely or are merely actors in a deterministic universe is one that has plagued philosophers for centuries. The idea of endless repetition may challenge our belief in individuality, in the uniqueness of the human experience. If everything repeats, is there room for growth, for real change? Moreover, the infinite repetition of everything also forces us to reconsider the nature of time. In a universe where every moment repeats, time no longer functions as a linear progression from past to present to future. Instead, time becomes a loop, a circle that folds back on itself with no true beginning or end. Our understanding of time as a one-way river is shattered, replaced by a vision of time as a vast, eternal cycle, where every point in the cycle is both a beginning and an end. This perspective challenges our deeply ingrained understanding of life and death, birth and decay, and the passage of time itself. Perhaps in the infinite repetition of everything, there is an invitation to live differently, to embrace the beauty and weight of every moment, knowing that it is part of an eternal flow, a dance that has been unfolding forever and will continue forever. The endless mirror reflects not just our actions, but the profound interconnectedness of all things, reminding us that we are part of a much larger, timeless rhythm that transcends our fleeting existence. In this cosmic mirror, every action, no matter how small, has eternal significance, reverberating through the infinite folds of time. The great unknown, the concept of beyond, is often framed as a distant horizon, a boundary waiting to be crossed, a mystery that beckons us forward. Yet what if the true nature of the beyond is not a place to be reached, but a permanent, unresolvable mystery, a silence that stretches endlessly through the cosmos? In this view, beyond the limits of our understanding lies not a destination, but an eternal enigma, a cosmic void that no amount of exploration, no technology or intellect will ever fully unveil. The silence of the infinite is not just the absence of sound, but the absence of closure, a mystery that is meant to remain, to defy our efforts to make sense of it forever. As we push outward into the universe, we encounter the limits of observation, the cosmic horizon. Light from galaxies beyond this point has not yet had time to reach us. and due to the universe's accelerating expansion, it never will. In a sense, the universe is always receding, always leaving parts of itself forever, beyond our reach. This boundary, while not physical, is a stark reminder of the inherent limitations of human knowledge. It is not just the edge of our observational capacity, but the edge of our ability to ever comprehend the full extent of the universe. We can build instruments to peer deeper, to measure farther, but there will always be regions where our reach fails, where the questions we ask go unanswered, where the truth remains locked away in the dark. This silent expanse beyond the horizon can be understood as a symbol of the limits of human existence itself. As much as we strive to understand, to discover, and to uncover the secrets of the cosmos, there will always be parts of reality that slip through our grasp. The silence of the infinite is a reminder of our fragility, that no matter how far we reach or how much we learn, there will always be mysteries too vast to solve. It speaks to a fundamental truth of existence that not all is meant to be understood, and some questions may be beyond our capacity to answer. Philosophically, the idea of the beyond as a permanent mystery challenges our human desire for meaning and closure. We live in a world that values answers, progress, and certainty. Every scientific discovery, every breakthrough in knowledge brings with it the satisfaction of having answered a question, closed a chapter, moved one step closer to understanding. Yet, the infinite silence of the beyond is a reminder that some questions may remain unanswered. The universe, it seems, may not always be a place of ultimate resolution, but a space of perpetual wonder and uncertainty. The silence is not a failure. It is an invitation to embrace the unknown, to accept that there are forces beyond our comprehension, beyond our control, and beyond our ability to define. In contrast to the finite questions we ask, the beyond as a permanent mystery shifts our relationship with the cosmos. Instead of trying to conquer the unknown, we are invited to live within it, to acknowledge that the universe is not a puzzle waiting to be solved, but a mystery to be experienced and appreciated. In this perspective, the silence of the infinite becomes something to be revered, not feared. It is a space where awe and humility meet, where the quest for answers is balanced by the acceptance of the unknown. The silence of the infinite also speaks to the nature of time. The universe is vast, and time stretches out beyond our comprehension, both in the past and in the future. The farther we look into the cosmos, the farther back we see in time, but we are always limited by the finite age of the universe. Similarly, the future, though it stretches on endlessly, is equally beyond our control. We can make predictions, but the ultimate course of time remains shrouded in silence. In this way, the beyond is not just a spatial concept, but a temporal one, representing the gaps in our understanding of the universe's past and future. Yet there is a certain beauty in this infinite silence. It invites reflection, urging us to consider our place within the greater cosmos. It challenges us to reconsider our assumptions about knowledge, time, and meaning, pushing us to look not just for answers, but for a deeper appreciation of the questions themselves. In the silence of the infinite, we find not despair, but a kind of quiet wonder, a reminder that the universe, in all its complexity and mystery, is far more than we can ever fully grasp. The true gift of the beyond, then, may not be the answers we seek, but the recognition that some mysteries are meant to be held, cherished, and respected in their endless silence. Living with the horizon, the cosmic horizon stands as both a literal and metaphorical boundary, a limit to what we can see, understand, and experience. It marks the furthest reaches of the observable universe, a point beyond which we can never travel, never reach. And yet perhaps it is not the crossing of this boundary that matters most, but the very act of striving toward it. Our meaning as human beings lies not in the final destination, but in the journey itself, the continuous pursuit of the unknown, the ongoing quest to explore, understand, and expand the boundaries of our reality, even if we never cross them. The horizon represents the unknown, the unknowable. It is a reminder that there are always mysteries beyond our comprehension, realms that are eternally out of reach. but it is also a symbol of the human spirit, our desire to stretch beyond what is known, to seek out new frontiers, to discover the limits of existence itself. In the face of this boundary, we find purpose in the pursuit itself. The horizon challenges us to question, to explore, to wonder, and to imagine. It is not in the crossing that we find meaning, but in the constant movement toward it, in the act of looking outward and asking, what lies beyond? As we peer into the cosmos, we confront the vastness of time and space, and in doing so, we are reminded of our own fleeting existence. We are small, limited, and mortal, but the horizon gives us something to strive for. It provides a direction, a goal that is not necessarily a place, but a state of being, a commitment to curiosity, to inquiry, and to the infinite potential for discovery. The horizon, in this sense, embodies the very essence of human experience, a constant striving towards something greater, even if it remains perpetually distant. This journey, while endless and often frustrating, is what gives our lives meaning. It is the pursuit of knowledge, the desire to make sense of our existence, and the willingness to confront the unknown that shapes who we are. The horizon teaches us that it is not the destination that defines us, but the questions we ask along the way. Our meaning is found in the questions, in the journey itself, and in the small steps we take to understand our place in the universe. Even if we never cross the horizon, we are constantly moving forward, inching closer to a deeper understanding of who we are and where we belong. In the end, living with the horizon is about accepting the inherent mystery of existence. It is about embracing the fact that some questions may never be answered, some boundaries may never be crossed, and some mysteries may remain forever beyond our reach. But it is precisely this uncertainty that gives life its depth and richness. The horizon, in its eternal distance, teaches us to appreciate the journey, to find purpose in the pursuit, and to understand that the quest for meaning is a path that never truly ends. It is the journey to the edge of what we know that defines us. And in this endless journey, we find our deepest sense of purpose.